So I think this statement is a bit hard to pass correctly, so I'm going to write it a bit differently to the way it is in my translation. If in a circle, a straight line through the center bisect a straight line not through the center. Okay, so as I said, I'm going to say this a bit differently. Let me draw the picture. So there's our circle, a straight line through the center. Make that CD. The center is E. Apologies, that won't give me room to actually give the statement. A straight line through the center meets a straight line not through the center. So that will be AB. Then the former line bisects the latter. So the line CD bisects AB if and only if it cuts it at right angles. All right, proof. Well, perform the construction as we've done it so far. AB does not pass through the center, so that means that this point of intersection between them is not at the center. I'm going to call that F. And obviously we're going to join EA and EB. Proving an if and only if statement, so let's suppose that CD bisects AB. That is, suppose AF equals FB. Then we have AF equal to FB, as I just said, and we also have EA equal to EB. So if we pay attention to these two triangles, they have two sides equal by what I just said. That is equal to that, and that is equal to that. And the base is equal in both cases, right? So it's a kind of strange way to say it. I'll just cite the relevant fact. So by proposition 8 from book 1, the angle AFE equals the angle BFE. But when a straight line, in this case CD, set up on a straight line, in this case AB, makes adjacent angles equal, they are both right. Okay, so that's by definition. So both of them are right. Okay, so that was one direction. Now for the second direction, it's basically the same argument. Okay, so when a straight line set up on a straight line makes adjacent angles equal, they are both right. So AFE and BFE are right. Okay, now for the reverse direction. So now we're not assuming that CD bisects AB. We're assuming that AB meets CD. Then you can draw the diagram and suppose that AFE and BFE are both right. Now we aim to show that AF is equal to FB. Okay, well, since EA equals EB, EAF equals EBF by proposition 1.5. If I remember correctly, proposition 5 says that if you have two sides equal in a triangle and an angle, if you have two angles equal in a triangle and one of the sides, then they're congruent. So we have, what do we know? So we're assuming there's a right angle, so that's BFE and AFE. Wait, no, I'm thinking of the wrong proposition. No, yeah, we're not up to that part yet. I'm skipping ahead. So proposition 5, we have that AFE and BFE are right. All we need is that they're the same. And we have EA is equal to EB. So the remaining angle has to be equal. Yeah. So proposition 5. It just says in isosceles triangles, the angles at the base are equal to one another. Okay. We also have the right angles. Sorry, so I made a mess of this. We're just using that they're isosceles triangles, right? So they share this EF, and EA is equal to EB. So the angles at the base are equal. That gives us EAF is equal to EBF. And then we have that these two triangles have two angles equal to two angles and one side equal to one side. So by proposition 26, the remaining sides and angles are equal. So AF equals FB, as claimed. All right, so the line is bisected if and only if the angle at which those two lines meet are both right. Okay, your turn, Kenneth.
Cool, thanks, Dan. So the next proposition, let me just attach a speaker. We're good. So proposition 4, I think that's what we're up to, is a very simple corollary of proposition 3. So we can do this somewhat quickly. So proposition 3, 4, it says the following. In a circle, so I'm going to paraphrase slightly. I think the way they had it is a little bit verbose. 2 lines, straight lines, not passing through the center. I guess when I say 2 straight lines, what I mean is 2 straight lines with their endpoints on the circumference of the circle. Yeah, so not passing through the center. Maybe that's what they mean by in a circle, 2 straight lines, right? Starting to spell the American way. Let's not do that. Center. Do not cut each other in half. Now, of course, there's no reason why they should cut each other at all. But in that case, I guess the statement is vacuous. In the event that they do touch, they do intersect, they don't cut each other in half. So let me draw the diagram. I'm going to draw a circle, and I'm going to have 2 lines inside the circle. I'm going to do this. Line number 1, line number 2, and we're going to use proposition 3.1 to find the center, which is here, and we're going to call it F. I guess this is, after we label all the other points, we'll get up to F, right? So this is guaranteed by proposition 3.1, says that we can find the center. Let me point the arrow in the right place. It finds the center. Right, I'm going to join up the center with this point of intersection of these 2 lines. And of course, I've drawn these 2 lines to intersect, and as I said before, they don't have to. But in that case, there's nothing to prove. So we're going to do the case where they do touch. Okay, so we're going to call the lines AC and BD. I'm going to call the line the point of intersection. Should one exist, BE, and we're going to draw the line from F to E as follows, like this. Okay, so that's the construction, and the proof goes as follows. The proof. So we're going to assume that these. I'm going to assume that E bisects AC and BD. So we're going to assume for a contradiction that AE is equal to EC and BE is equal to ED. Okay, and so what did we just prove? The previous proposition allows us to say something. Proposition 3, 2, 3, right? Excuse me. By the previous proposition, FE hits both AC and BD at right angles. At right angles. And of course, that's because we've kind of assumed that these FE bisects these lines, right? So it hits them at right angles, i.e. FEA, the angles FEA and FEB are both right angles. Just saying the same thing with labels. In particular, they're equal, right? And we can see that that's not possible because these two angles, well, either one is part of the other. Well, one is part of the other, right? So this is impossible. Because, well, what I was to say, F in the picture, the way we've drawn it, FEA is part of FEB. Of course, this could be reversed depending how we label it. Part of FEB, right? And so this is impossible since we assumed they were both right angles. And so, of course, what this means is that the two straight lines don't bisect each other. So AE equals BEC and BE equals ED does not hold. That's it.
Nice. Not often
that was
we
a good
finish with 10 minutes to spare.
Yeah, right.
I should have actually looked at proposition 5. We could probably fit it in. Let me have a quick look. Shall we try?
Luck would have it. 5 might be super long.
Nah, proposition 5 is short. Let's do it. We've got 10
up to you.
I didn't read it, but I'm sure we'll be fine. Okay, just stay attached to speaker. It doesn't matter. Okay, it says if two circles cut one another.
Yeah, that's pretty short. Yeah.
They will not have the same center. Well, if we want to get through all 13 books before we turn 60 years old, we have to get a move on.
Yeah.
Not that's a bad use of the next, 20 years of our lives, but okay, proof. All right, so here's our two circles. We're going to call them CDG. D is just some random point that is used to label the circle. And A is similar. Okay, so let circles A, B, C, C, D, G cut each other at BC. Remember, there's a distinction between cut, which means transverse intersection in modern language, and touch, which is non-transverse. That was sort of discussed in the definitions. I won't reiterate it. So this is the kind of picture we're considering, and we need to prove that they do not have the same center. I like the way he says, for a contradiction, it says, for if possible, let it be E. I think that's kind of a slick way of saying it, so I'll copy that. For if possible, let it be E. So in modern terminology, for a contradiction, suppose that in fact they did have the same center and call it E. Join EC. Okay, so here's our E. We're going to join EC. Oh, yeah, I guess my picture makes it too obvious it's false. So let's try again. The circle should contain its center, right? There's my wonky circle. That's A, C, B. Suppose they have the same center, then of course the center is inside both circles, so this is the appropriate picture. Join EC. Let EFG be drawn through at random. Great, okay. Yeah, I don't know what to say about that. At random, really? Could I draw it over here? I don't think so. I have to pick a point between B and C, but on which side? Yeah, okay, I wish I had read this earlier so I had something intelligent to say. Let's just follow it. Okay, EFG. Since E is the center of ABC, EC is equal to EF. Yes, because E is the center of the left-hand circle, so to speak, and those are both radii. And since E is the center of CDG, just keep an eye out for the argument in whether it really matters that this is sort of like over here, so to speak, versus over there, because that distinction is not something that belongs to the picture. It's not a real thing unless we prove it is so. Since E is the center of CDG, EC equals EG. Yes? But EF therefore equals EG, lesser to the greater, which is impossible. I find this argument very suspicious. Hence, the centers are not the same. Okay, let's try and rescue this pseudo-proof. Okay. I mean, clearly these EF and EG lie on the same line, so you could say, well, one of them... Okay, let me try and say this in a way that it's actually legitimate. So we have two circles, they cut, let E be the common center, join E to one of the points of intersection, and then draw any other line through the center of one of the circles. First of all, I claim that other line, it's possible to find such a line that cuts the other circle. So this is like our primary circle, let's call it. This is the primary circle. Join a line from the center to one of the points of intersection with the other circle. And then, well, clearly, I guess, the other circle has some part inside the primary circle, and you draw a line through the center of the first circle that meets the other circle. Call that EFG. Then, by construction, EF is less than EG. If EF were equal to EG, then they would touch, right? They wouldn't be transversely intersecting. They would cut at C and B, but also be touching at G if EF were equal to EG. Okay, so the proof is fine. It's just contradicting. The contradiction we reach was to the hypothesis that they only cut each other and don't touch. So it wouldn't apply in this situation, for example, where I had a greater circle like that. I mean, we haven't proved that circles can't both cut and touch, right? As far as I know. Yeah.
I don't see why we need C, right? You have the line EG, and what is it? EF should be equal to EG, right? I guess you need an external point, right? So I guess the fact that it touches means that you can find the external point G. Right? Like you can do this without C, right? As long as you have EF.
I didn't really do anything. Yeah. That's true.
But maybe EC is meant to be like well, they say it's equal to EF, and EG, wait, yeah, right?
Yeah, but as you say, like basically, like the real argument is the one I said, right? Which is that EF is less than EG because that part of the circle lies inside there. But so that's
right.
Yeah, I'm not actually sure this is a proof, or at least I feel. I mean, there's often wiggly bits in these proofs, but this is the proof we've seen so far that worries me the most in terms of it relying on
right.
like this idea that the circle, once it cuts at C, it's sort of like staying inside the other circle. I mean, I think we can. Yeah, I think we could fix it. But yeah, I feel a little unsure. I think this is resting a bit on implicit statements or understanding of the behavior of two circles when they meet from the picture.
Right.
But yeah, we'll leave it at that. Okay.
Cool.
Nice. 3.
Yeah. Cool. All right. I guess I'll catch you later tonight, Dan.
Yep. See you later.